Hello Internet, my name is Quinn and this is Blondihacks. Pressing forward this week on the running gear for the Pennsylvania A3 switcher locomotive. Very exciting day, as you've already deduced from the thumbnail, which is that we're going to see this locomotive sitting on her drivers for the first time in this video. We got a lot of work to do before that though, so let's go. Here once again is the frame. Of course we got the suspension going with the front axle box. Now it's time for bearings. Bearings for this locomotive are going to be made from 932 bearing bronze, which I have some of here. We just got to make this go into there and also there. Now I started with round stock because we're making round bearings and that seemed reasonable to me. I even cut a piece of it off and started planning out my order of operations and then realized I cannot start with round stock. Somewhat counterintuitively for these bearings, we have to start with rectangular bar stock. I happen to already have this beautiful piece of 932 bearing bronze bar stock in my bin. Now it's a little bit too thin to get an entire bearing out of one, but that's okay because we need to make them in halves anyway, as you'll see. So what I'm going to be doing is cutting strips off of this, and each strip is going to form the top half or bottom half of two bearings. Bear with me here, as it were, and you'll see how this is all going to work. This order of operations was based on what Kozo suggests in the book. However, he's got a few steps towards the end of his process that I actually don't necessarily agree with. I think he's doing it that way because it simplifies some of the turning operations and requires simpler tooling. But I think with my experience and with the tooling that I have, I can do a slightly improved method, as you'll see. Initially, I started with round stock because Kozo starts with square stock, and I didn't understand why he was doing that. It didn't seem to make any sense. But you'll see in real time the steps that I had to go through in my head before starting this, and I slowly came to see why Kozo does each of these steps that he does. I'm going to start by doing a cleanup cut on all four of the long axis faces of each of these little rectangular strips. Now, I don't actually have to square everything up perfectly. Really, the only goal here is to get clean faces on the two larger sides of each of these pieces, because these pieces are going to be stuck together and we're going to turn the bearings out of them. These are split bearings, and what that means is we have to have a split line that runs exactly down the center of the round profile of the bearing, but with no kerf. So you can't make a solid bearing and then cut it in half. It has to be a zero kerf split line, and the surfaces inside that split line have to be machined so that they mate perfectly together. So that's why we have to jump through all these crazy hoops to make these bearings this way. My goal at this stage is to get these two bars to be machined top and bottom on the wide sides and be exactly the same thickness. You'll see why in a second. The short sides don't actually have to be machined. It was just easier to do it in order to get the opposite sides parallel and to an exact thickness. This stage is also why we have to start with square stock, because we have to be able to get those pieces to the same thickness and machined front and back. And we can't do that if they are half rounds. A half round is just about impossible to fixture in the mill. So starting with square stock actually makes sense once you get to this stage in the working it out process. I'm now prepping and very carefully supergluing these parts together. Kozo uses soft solder for this, which is traditional, and obviously works just fine. In fact, probably a little better. But, well, I'm impatient and I really like superglue, and the cleanup from superglue is a whole lot easier than soft solder. The secret to doing this with superglue is to prep the surfaces well, make sure they're clean and degreased, and clamp those parts together for at least 15 minutes. Even longer is better, because we're kind of at the limits of the strength of superglue when we're doing stuff like this, and if you don't do all of the prep just right, then the glue will fail, and probably scrap your part in the process. Now I'm clamping it up in the forejaw, and I'm going to be dialing it in just like you would any piece of rectangular stock, but I actually only care about these opposite faces, the faces that are a little wider. Recall that on this axis, these two halves are the exact same thickness. So dialing in this axis of the glued up assembly is a proxy for getting the center line, that split line between the pieces, exactly on center on the lathe. It only matters on this axis. You'll note on the other axis, the parts aren't even very well aligned. It doesn't actually matter because we're going to be turning all that away. All that matters is on this axis, the split line is exactly on center. This is going to make more and more sense as we go along if you're having trouble. On the short axis, I did dial it in approximately, just, ballpark within 50 thousandths or something, just to make sure we have enough material to turn off. We don't want to run out of material and not be able to get a round bearing out of this entire assembly. Speaking of which, let's now get a round bearing out of this entire assembly. As is tradition, I'll start by facing it off. This facing cut's really important. This is going to be the thrust face of the bearing. These bearings not only hold the axles and act as radial bearings, but they actually act as thrust surfaces for the backs of the drivers as well. So this surface needs to be well machined, and it also has to be extremely square to the bore through the bearing, which we are going to get because we're going to do it all in one setup. Now we can turn down the OD. Because that bar stock I started with was quite a bit thicker than half a bearing, I have a lot of material to remove at this stage to get down to dimension, but I knew that was the case and I intentionally left it to do here on the lathe because I can remove that material much, much faster on the lathe. It has to come off at some point, so better to do it here where I have a rigid machine that can take heavy cuts. Getting close now, one finishing cut, and we should be to the OD of the flange, the thickest part of the bearing. And that dimension's looking good. Here's where I differ from Kozo. He has you cut the flange on the headstock end of this part. I'm going to cut the flange on the tailstock end because that's going to allow me to do the entire bearing in a single setup for maximum concentricity throughout. So I'm going to cut the back portion of the bearing with a grooving tool. So I'm going to find the end of it there and then translate in a little bit more than the thickness of the flange, and I'm going to cut that inner diameter with a grooving tool. Kozo does this the other way. He has you put the flange on the inside so you can do this diameter with a regular turning tool. Then he has you part it off and do the flange in a second operation using a kind of homebrew crush collet fixture that he suggests. I started off using my standard go-to grooving tool, and I really didn't like how that was cutting. This is a grooving tool for steel, so it's got a 10-degree top rake on it, and that's really too much for bronze. Bronze and brass do not like top rake at all. They're very grabby, they don't cut very well. I went and ground a proper zero top rake grooving tool for brass and bronze, which I've needed for a while. I've been struggling through using the wrong tool for too long. Now, pro tip, when you're grinding a grooving tool, bias it to the left rather than centered as I've done here, because then you can get really close to shoulders and the chuck, and that is frequently the difference between being able to finish a part or not in my experience. In this case, I forgot which side I was supposed to be grinding, and by the time I realized I'd taken too much off one side, so I ended up with a centered grooving tool. But here we are. If you've watched any of my other engine builds, then you've seen this technique before. This is one I do a lot. I'm plunging to a little bit short of the final dimension in multiple passes down the length of the diameter, and then when I get to the inside, I pan across, and that evens out all of the plunge cuts, and also corrects for any slight geometry errors that might be in the grooving tool. If it's not quite square, or there's a little bit of a cup, something like that, then panning across cancels all that out, and you get a nice, perfect, clean diameter. Then I go to just inside my flange on dimension, and I face the back of that flange, go to final dimension, and then do one more series of plunge cuts if needed, and then finally do a pan across very lightly to clean up the surface and even out the diameters. This technique works really well for me. It is a little bit more complex than a simple turning operation though, which is probably why Kozo has you do it the other way. But by doing it this way, as I said, I'm going to get maximum concentricity because all of the bearing features are being done in one setup. When you're talking about bearings, you really can't have too much concentricity. The better it is, the better those bearings are going to run. Now I can center drill and drill out the center. I'm going to just get rid of most of the material with drills, and then I'm going to finish this inner bore with a boring bar. I think in the book Kozo suggests a reamer for this, but I do actually have a boring bar that will get this done, and by finishing with a boring bar, again, I'm getting maximum concentricity. Using a reamer for this is very convenient because it's easy to hit the exact dimension you need. However, the reamer is subject to whatever wander was in the drills, because reamers can't create concentricity. They're a multi-point cutter. They're going to follow whatever those drills did. And drills pretty much always wander a little bit, especially when center drilling onto a split line as we're doing here. That center drill always catches the split line a little weird, and the drills tend to wander a little bit, and you're going to lose some concentricity. So a boring bar at the end will correct all of that. Speaking of which, I've got my gauge pins here. These are the bottom and top of my tolerance, and I've got a series of gauge pins that are smaller than the bottom of my tolerance as well, so I can kind of sneak up on the dimension using gauge pins as my metrology. Measuring tiny bores like this accurately can be difficult. For me, what works the best is just a big stack of gauge pins on the side of the lathe. I've also learned the hard way to always touch up the boring bar on the front of the piece and then do a dry run, go into the depth that you think you need with the boring bar with nothing running. because I have more than once crashed a boring bar into the bottom of a hole that was not as deep as I thought it was, or commonly the end of the drill cone is a lot shallower than you think it is, and your first couple of cuts end in tears. There's no crying in machine shop. This first cut is really just getting rid of any runout that might be in the hole from the drills. We're regaining any concentricity that we lost from those more primitive tools. The boring bar is a sophisticated hole-making tool from a more civilized age. For this operation, I'm also taking spring cuts on my way out. And if you've watched my channel, then you know that I usually don't like to do that with boring bars because they're typically carbide inserts, and carbide inserts don't like taking really light cuts. However, this happens to be a high-speed steel insert. This is an Arthur Warner boring bar with a high-speed steel insert in it, which does like very light cuts. And so doing a spring cut after each pass ensures that I'm measuring the dimension that I think I am. I now work my way through the stack O gauge pins to find out what the dimension of this hole is right now. And we are at 436, which is actually just 2 thou below the bottom of my tolerance. So got a little lucky there. That was a bit close for comfort. What that means is the drill wandered a little more than I thought it was going to. So for subsequent bearings in this setup, I made 4 of these. I actually went down a drill size to give myself a little more wiggle room, because if that drill had wandered even slightly more, I would not have been able to clean up this hole and regain concentricity without blowing the dimension. So you gotta watch that. Machining is frequently a tug-of-war between efficiency and not blowing your dimension. The smaller drill means more passes with the boring bar, so it takes longer. When you do it right though, magic happens. There's the bottom of my tolerance right there, and look at that. That is just a perfect fit. Gosh darn it, that never gets old. That is why machining is the second greatest hobby, second only to model railroading. This is the actual axle material that I'm going to be using. This is precision ground stainless bar stock, and so I'm also test fitting on that to make sure that my axles are going to be a nice fit, which they are, so we can move on. And here, if you look closely, you can see the split line on the bearing still there. Pretty cool. Hopefully it makes sense why all of these convoluted steps were actually necessary to achieve that. There are other ways to make split bearings, I will say, but this is the method that I landed on. It's, like I said, a mix of what I thought would work for me and what Kozo suggests, and it does seem to have worked. But I'll never claim this is the only way to do it. I'm ready to part this off, and make sure to stop and deburr the back of that now, because this is about to be a very difficult edge to deburr. And Yahtzee, whoa! Look at that, right as the parting blade broke through, the super glue failed on the mating surfaces, and I got my bearing halves. Perfect. That worked out, but this is where soft solder actually would have been better. Soft solder would have been strong enough to hold those halves together. With the super glue, there was so little surface left that it just wasn't strong enough anymore. But I got away with that and just had to do all of that 4 times. And by 4 times, I mean 7 times. This was one of those days where everything went wrong. After that initial success, I blew the dimension on the second one because I swapped a 6 and a 9 in my head in a moment of dyslexia. On the second one, I misread the DRO and completely blew the inner dimension. Didn't even bother parting it off because it was already scrap metal. The one after that went perfectly. I got 2 beautiful bearing halves, but then just as it was flying off the parting blade, the second half flew up in the air and got caught between the chuck and the tool post, mangling it. Yeah, I had some words for the universe after that one. Actually, just the one word. Really? Come on. Okay, I guess that was 3 words. But after all that, I cranked out 3 more flawless ones first try. Sometimes you just got to make all the mistakes on a part up front, and then you're really good at it and you can crank them out. Let's give these a test fit and see how it goes. It's interesting how sometimes the simplest looking parts are actually the trickiest to make, as you've seen so far here, I think. You can see how the lower half goes into the frame like so. That'll actually get Loctited in place so it doesn't spin. And then the other half goes in the bearing cap. And then the whole thing clamps down like so. And being a split bearing, there's room for adjustment here. If it's too tight, we can shim the cap a little bit. Or if it's too loose, or if it wears over time, we can remove a little bit of material along that split line to clamp it down a little tighter. So there's lots of adjustment built into these bearings, which is important because of course they are the main driver axle bearings. Looking at it from the front, hopefully you can see how there's kind of room to adjust everything as needed on all these different mating surfaces between the bearing halves and where the cap meets the frame and so on. Those are all adjustment points. Up here on the front, of course, we have the pivoting axle box, but otherwise it's the same story. The axle box is the bearing carrier, so one half gets Loctited in the bottom, and then there's a bearing cap that sits on top. If you look closely in this shot, you can see how the lubrication system works. You might recall we drilled these angled lubrication holes in the axle box, and you can see that what it's doing is it's depositing oil on the axle right behind the bearing. And so it's going to work its way into the space between the axle and the bearing from back here. That way we don't need a lubrication channel or anything in the bearing itself, which would have, again, complicated manufacture quite a bit further. On initial assembly, things were a little bit tight, so what I did is I clamped everything down to full tightness, torqued it down as it were, and then ran a reamer through by hand that's the same dimension as my axles. This just makes sure that when everything's clamped down for the first time, everything's going to run smoothly, and then we can adjust for wear from there. I didn't want to have to start with shims under the bearing caps. I'll test fit my axle stock in there now, and that now slides nicely in there. That's certainly an improvement. However, it's still running a little stiff. It's at a point where it would run in from here. However, what I'm going to do is actually kind of an automated run-in, because I'm going to be building all of the valve gear and so on from here, and I don't want the axles to be stiff and thus make it difficult to determine if I've got sticking mechanisms in the valve gear or other subsequent systems that are going to be attached to these axles. So I want the axles to be running freely from the beginning. To that end, I'm doing kind of a pre-run-in break-in procedure. I just put the axles in there with some light oil and spun it up for a while to simulate what would happen the first, several hours that this locomotive is running. If it had been tighter than this, I wouldn't have done this, but I can tell from experience that it was just at the point where it will break in nicely. And that procedure was perfect for the front. Now that's running smoothly in there, nice and free, very nice. The rear was still a bit too sticky, so I kicked it up a notch and I put a little bit of lapping compound on that axle and then ran that in there just for a few seconds. Like lapping compound on bronze, it's pretty aggressive. It doesn't take much, just a few seconds of that. And then I stopped, I pulled it all apart and very meticulously cleaned everything out. You really don't want abrasive grit from lapping compound sitting in your bearings. So I cleaned everything out very thoroughly, and that was all it needed. Just a few seconds of that lapping compound, and now that rear axle spins just as beautifully as the front did. Success! Let's actually go ahead and make some axles now from this bar stock. The nice thing about the main drivers is that the axles are incredibly simple. So much simpler, in fact, than even the tender axles, which had quite a few features on them. They had a bunch of shoulders and different diameters that all had to be just right. The main driver axles are actually literally just bars with faced ends. That's why I started with this precision ground stainless bar stock, because it's going to save me a bunch of operations. All I got to do is clean up the ends and face them down to length, and we're done. Gotta like that. Accurate length is, of course, very important though for these parts. I'm going to do the 3-stage procedure that you've seen me describe a lot on this channel. I'll describe it one more time because I get a lot of new folks on every video, and this is one of those things that stumped me as a beginner. How do you face something to a really specific length on a lathe, because you can't measure the part when it's in the lathe? Well, you face one end, you flip it around, you face the other end, then you take it out and you measure the length where you are now from 2 machined faces, then you put it back in, touch off carefully, and remove the remaining amount based on your measurement. It's a bit of extra steps, but if you need an accurate length on a turned part, this is how you got to do it. It's also important to chamfer after each facing cut when doing this to make sure that any burr on those facing cuts does not interfere with your measurement. In this case, I'm doing extremely light file work when I do that deburring, because the drawing is very specific that there should be no chamfer on the ends of these axles, presumably so that they'll be flush nicely with the drivers when it's done for appearance. But so I'm trying to, when I file, just knock the burr off without actually creating any chamfer on that. Just a couple of light swipes is all it takes. Next up, I got my dial indicator in here, and I'm going to see how concentrically these shafts are running in my collet chuck. We need to put centers in the ends of these axles, both for appearance, because locomotive axles always have centers in them, but also it's just always a good idea to have centers in axles and shafts. And this is actually running within 1/1000ths, so that's good. You might be wondering why I bothered to check that. Well, this is a homebrew collet chuck made from garbage off eBay, and while it should be good in principle, it's a collet chuck, sometimes it misbehaves and it's got a little more run out than it should. But luckily this time it's behaving itself, so I didn't have to get out the forejaw and really dial these in. That center drill raises a little bit of a burr, so I made sure to knock that off with a file as well. The reason you always want to have centers in axles is, well, for appearance, because traditionally axles are going to be made between centers, and so that centers would be there as part of manufacture. But even though we didn't need them for that reason, you still want them there for later rework. If you ever have to regrind or balance these axles or do any kind of future work or repair on the wheels or axles, you're going to need centers. So put them in now, and future you will thank past you. Those axles came out really beautiful. Very happy with those. Of course, some centerless grinding machine in whatever steel yard McMaster uses gets all the credit. All I did is whack them in half and punch some holes in them, but still, they turned out really nice. Now, what should we put on the ends of these axles? Well, I don't know, I'm out of ideas. Good video, thanks, I'll see you next time. I'm just kidding, of course we're going to talk about the wheels. But let's talk about wheels, because they are the cast iron elephant in this room. I know that many of you have been waiting, possibly since the beginning of this project, to see me machine these wheels, because certainly locomotive wheels are one of the most charismatic and distinctive features of a steam locomotive. They really are beautiful things. And here they are, fully machined. I know, you wanted to see me make these, but hold on, allow me to explain. Back at the very beginning of this project, when I started it, I had a bunch of viewers who offered to send me parts for this locomotive because they had started the A3 as well. It's a popular choice for first-time locomotive builders, and for whatever reason, health reasons, loss of interest, financial, whatever, they weren't able to finish the project, and they wanted to donate the parts that they had to my project. I'm super grateful for all the folks that did that, and these drivers were among those parts. Now, in the book, Kozo actually walks you through making wooden forms for these drivers, and then he has you send them off to your local foundry that he imagines we all have. I would not have known how to do that. There's certainly no cast iron foundry anywhere near me that could do this. However, this locomotive build is so popular that there are a bunch of companies that make these castings. And the fellow that donated these to the channel had bought those castings from one of those companies, and he has machined them to this point. And honestly, they are beautifully done. They are machined easily as good or more likely better than I could have done. So I'm grateful to have them. But as you can see, they are a standard railroad wheel profile. There's a cone on the tread, and then there's also a cone profile on the flange at the back and various radii and things. And you are not missing out because the process of machining these is exactly the same one that was used for the tender wheels. So if you want to see how this was done, go check out my tender series where I machined the flanges, as you see here in this old footage, with the compound at an angle to create the cone profile. In this video, I also went deep on the whys of railroad wheel geometry. It's fascinating, and you see all the steps for creating it in this tender wheel section. These drivers are done exactly the same way, except that we're starting with a casting instead of a solid slug of steel. Really no difference. The only thing left to do on these drivers is the part that's unique to drivers, which is the crank pin hole. That has not yet been done on these, so you will get to see me do that. However, I'm out of time on this video, so that's going to have to wait, but I can't not put them on the axles at this point, right? So let's give that a whirl and see how it looks at least, even if we can't permanently attach them yet, because we still have eccentrics to make for the water pumps and various other things inside the frame. And yes, steam nerds, I hear you yelling at your screens. We will, of course, be quartering these wheels. It's a very important step. We're going to get to all of that. But let's just have a look at her on her wheels for the first time. The other cool thing is that we can now see how the suspension works on the locomotive. You can see as the front axle box tilts, it lifts a rear wheel as needed to keep 3 drivers in contact with the rail. Now this is heavily exaggerated. The normal motion is so small you can't even see it, but I'm exaggerating so you can see the effect. If it ever needed to move this much, well, you've got bigger problems than suspension contact, and you better have some strong words with your track maintenance crew. Of course, I can't resist rolling it a little bit as well to pull the tender for the first time ever. I don't want to do this too much because the wheels are threatening to spin on the axles because they're not attached, and I don't want to wallow out those holes. I also had to set the boiler on there one more time because once you've got the drivers and the boiler, then you really get a feel for what the final locomotive is going to look like. It's really starting to look like a boat now. Sometimes the most work goes into the simplest looking components, and these split axle bearings were a great example of that. I'm very happy with how they came out though. All of the patience paid off. All the dimensions came out great, including the very vital flange thickness, as you can see, because these flanges form the thrust surface that the drivers run on in the back. Everything lined up just right with the length of the axles. Couldn't be happier with all of that. It was a frustrating couple of days making those bearings, I'm not going to lie. The struggle was real when I was scrapping part after part after part. But that's how it goes sometimes in machining. You just got to stick it out and get it done right, especially with something as important as main axle bearings. Well, thank you very much for watching. Thank you so much for all of your support, especially to my patrons who make all of this happen every week, and I will see you next time.